Mahmoud's presentation tonight is on dynamic portfolio optimisation and asset pricing, martingale methods and probability distortion functions. Would you welcome Mahmoud, please?
First of all, I would like to take this opportunity to thank the organizers of this wonderful event for giving us the opportunity to stand up here and share our research with you. I'm going to talk to you about, well, briefly because I have only 15 minutes, about dynamic portfolio optimization using martingale methods as compared to stochastic dynamic programming, and about asset pricing using a recently developed technique called probability distortion function approach, and to see what's the link between this approach and martingale theory. This research was under supervision of Professor Mike Sherris and with the help of actuarial studies staff at the University of New South Wales, as well as Dr. John Vanderhoek from Adelaide University. This research was motivated by the convergence of financial and insurance markets, which started by trading insurance products on capital markets, such as catastrophe futures, weather derivatives, energy risk securities, and other products as well. So with this convergence, there is a major concern about consistency between the actuarial pricing principles and financial theory. In financial theory, to price an financial product, one starts by setting up a model for the underlying security process, usually via an SDE under the real-world probability measure. Then one chooses a numeraire and changes this real-world measure into an equivalent martingale measure, under which the asset prices discounted by this numeraire are martingale. Having done this, pricing any derivative, or strictly speaking, pricing any attainable contingent claim, will involve taking expectations under this equivalent martingale measure. This, of course, works fine if we want to price if the derivative is attainable. When the contingent claim is not attainable, some techniques like utility maximization, where we imagine all investors in the market acting so as to maximize, trading, selling and buying assets so as to maximize their expected utility of consumption through time. In this economy, in this setup, an equilibrium prices will imply and will use these prices for non-attainable contingent claims. However, this method has got problems because of the modeling of preferences for investors, and then also for calibrating the utility functions if that model was chosen. In insurance world, this is different because the financial theory assumptions do not hold. We know that insurance claims are typically heavy-tailed in a sense that extreme events might occur with higher probability than in financial world. The market is incomplete in a sense that you cannot replicate or you cannot hedge an insurance claim by investing or trading in primary securities in the market. So the whole financial theory cannot be applied straightforwardly for insurance markets. On the other hand, applying techniques such as, actuarial principles such as standard deviation principle, expectations, variance principle, seem to be not satisfactory for pricing insurance derivatives. So going from this perspective, Wang introduced the proportional hazard transform to price insurance products and has extended this proportional hazard transform to a wider class of probability distortion functions. And the name probability distortion functions comes from the fact that we distort the cumulative distribution function. Do you have another microphone? The name of probability distortion functions comes from the fact that we take the risk premium to pay for a contingent claim X as the mean of distorted decumulative distribution function of the claim X. And the distortion probability function is based on standard normal CDF. And alpha is a parameter that can be taken by calibrating the underlying security process. So this approach does not assume any distribution for the underlying. No log normality assumption for the underlying is used here. If you have an insurance product, you just take the cumulative distribution, 1 minus CDF, and distort it, take the mean, and this is the price to pay for that risk. And it turns out that this is consistent with Yari dual theory of choice under uncertainty developed in 1987, where he starts from the basic axioms of utility theory and changes one axiom, which is independence, to a dual independence axiom, and all the theory holds afterwards. The first question that we address here is, using such risk measure implied by Wang transform, can we have, thank you. Using such risk measure implied by Wang transform, can we have the same option prices as in financial theory? In other terms, if we use this risk measure here and we apply it to, let's say, a call option on the underlying, will we get Black-Scholes option prices? We can prove mathematically that when the underlying security process is geometric Brownian motion, then we obtain exactly Black-Scholes option price. And we can even extend this to the case when we have time-dependent mean and diffusion terms in the underlying diffusion process. With modification of this certainty equivalent, we can obtain also Black-Scholes, extended Black-Scholes option prices. However, when we move away from normality, which is typically the case for insurance, then this consistency does not hold anymore. And the example for that is that we took in our research is the CEV model for the underlying asset. So when you have an asset with constant elasticity of variance diffusion process, we know that from Black and Cox's paper, we have closed form solution for option price written on that security. And when we apply Wang transform to this process, we do not have the same prices. The prices are close, but the difference increases as we go deeper out of the money in the option. So that led us to consider a modified or generalized Wang transform, where instead of taking the standard normal cumulative distribution function, we consider the CDF of the underlying security process. Because the idea here, this is consistent with financial theory in the normal world, and this comes from using the CDF of normal distribution. So if we move away from normality, naturally we have to consider CDF of the underlying security process. And it turns out that the discrepancy between option prices using this new or generalized Wang transform give us better results than using normal CDF. So all of this here, we can consider it as a step forward into finding a unifying framework to price insurance and financial products. And this comes in line with the convergence of financial insurance markets. The only thing we have to use the probability distortion function wisely in order to have consistency. The other part of research considers comparison between martingale methods and stochastic dynamic programming in doing asset allocation. The idea of stochastic dynamic programming is to solve backward in time for the optimal consumption and investment strategy many times as your periods are. The idea of the martingale approach is to solve first for the optimal consumption using one optimization problem, then work out the optimal trading strategy that finances this optimal consumption, as in option pricing technology. In the thesis, we examine cases when it is better to use one rather than the other, and we also propose implementation of the martingale approach for discrete time in binomial and trinomial lattices. Another question that arises is when you use the closed form solution of the continuous time optimal investment and consumption strategies, people do not, in practice, trade continuously in time, so they have to discretize this solution to fit their objectives. We solve this optimal trading allocation and consumption allocation discretely in time, and we compare it to the discretized continuous time solution and see the differences which are typically arising in the edge of the lattice if it is not trinomial or binomial lattice. So these are the two parts of the research, and the third part was applying this technique, the martingale approach technique, to solve for the optimal consumption and investment strategy problem using an objective involving proportional hazard transform as well as the probability distortion function approach. So I finished my PhD last year, and now, besides working in industry, this research is still going. And now I am investigating with people in the actuarial studies department how we can use the Wang transform, the generalized Wang transform, when we have different underlying security processes when the dependency is modeled via copula structure, where, in example, we take elliptical distribution, and also when we take this generalized Wang transform with the underlying having stochastic volatility model, as in Henderson model, and we aim to compare this result to the setup when we have to minimize the maximum likelihood density as a dual utility maximization problem, as demonstrated by Schachechmeier in his paper. So the idea is to extend this research to general framework which fits insurance markets and compare that to financial markets. If you are interested, you can download the thesis from my website and give me, if you have time, some suggestions. Thank you very much.
Mahmoud, we do have time for a few questions.